Good morning, everyone. Already having been introduced, I guess I don't need to introduce myself. I am joined today electronically by Dr. Mohammed Hagnagadar. He's on Teams on my laptop. He was a part of the team that worked on this, as well as Dr. Maxime Larin and Jens Hetzer on our side, then of course Sam and Rosemary with CPFD. You may or may not have heard of Schmidtsche Schack before. You may not or may not even want to try and pronounce it. If you don't want to try and pronounce it, our parent company is Arvos. We're happy to hear Arvos just as much as we are to hear Schmidtsche Schack. So we've been in the critical heat transfer solutions business for 110 years. Depending on the year, of course, 150 million of revenue. That's probably one of the better years if we're being honest. About 400 employees worldwide. The largest location by far is in Kassel, Germany. That's north of Frankfurt, about an hour and a half. That's where our headquarters are and our manufacturing shops. We've got actually two different shops there where things are manufactured. Then an engineering center in Dusseldorf. So Mohammed is based out of Kassel, and Maxime Larin, who was on the previous slide, is in our Dusseldorf office. I am 1/3 of the Houston office. Well, it's a small satellite office. We have a bit larger presence in Wexford, Pennsylvania, about 15 people there. An engineering center in Mumbai, as well as a sales office, and then sales offices in Shanghai and Kobe. So we produce high temperature and or high pressure heat transfer solutions in a wide variety of industries. Petrochemical, waste to value, refining, metallurgical, and chemical. So it's a small part of a chemical process in a bigger chemical plant that probably makes something that definitely doesn't sit on the Walmart shelf, but it goes into something that is sold at Walmart, for example. The work that we did with CPFD on the Barracuda virtual reactor was for a piece of equipment that we sell into renewable gasification applications. So on the left-hand side is a very high-level overview of what this process would entail. So you would take biomass or municipal solid waste and do some feedstock preparation on it, and then it would go into a primary gasifier first, and that would take that material and convert it into what I would call crude syngas. So it's a combination of carbon monoxide, carbon dioxide, hydrogen, and water primarily. And then the adventure is in all of the other little, I'll call them cats and dogs that come along for the ride. Things like tar, ash, other particulates. You might get a nail or other challenging things to work with. And we come next in the process. So we sell a solution that uses partial oxidation, or POX for short, to take that crude syngas and upgrade it to a more usable product that has more carbon monoxide and more hydrogen and less of all those cats and dogs that I mentioned earlier. So in the piece of equipment there, you see in the middle that POX reactor is approximately the top 1/3. It's a very high temperature, maybe not the hottest process there is in the world, but we're talking like 1500 C or 2500 Fahrenheit. It can be lots of different pressures. It depends on the application, from atmospheric pressure up to 60 or 70 bars is common. Probably not for the biomass or waste as much as maybe natural gas. And then the second 2/3 at the bottom there is what is called a radiant syngas cooler, or RSC for short. So we're pulling out as much of that heat of reaction and getting the gas into a condition that other equipment can handle it, first with that piece of equipment, and then of course there's further process steps downstream like filtration, water scrubbing sometimes, to take that, again, syngas from a crude syngas before that may be laden with tars, ash, things that you don't want to send to your Fischer-Tropsch unit or your methanol plant, and get it down to a manageable temperature, take the solids out, and move it along in the process. So as far as the simulation side of things, obviously this is fairly complicated equipment to simulate. There's quite a few different reactions going on there. It's not just as simple as, there's a partial oxidation reaction, there's combustion reaction, there's water gas shift reaction, and then there's a whole host of other reactions going on there. And I won't bore you by listing them all, but of course, generating a model for this for our purposes and for our customer purposes is our goal, and we try to continually improve it. On the next slide, I've got a cutaway view of that same piece of equipment. It's probably a little bit easier to envision that way. So at the very top, you have a feed injector. You have what most people would consider a flame in the middle of the POX reactor. So the crude syngas is actually entering on the side of that feed injector, and it's combined with oxygen and usually another fuel that provides heat for, some of these reactions are exothermic, but the majority of them are endothermic. So you actually need to introduce some heat there. But you've got particles, you've got a reactive gas and syngas with all that carbon monoxide and carbon dioxide. What we're really trying to do is crack that tar and make it something usable like CO or CO2. Is much more useful for the downstream processes than tar. And of course, tar makes a really good mess too. And unconverted carbon is another unique selling point of this process. So we can actually take small carbon particles and convert them into usable carbon monoxide or carbon dioxide with this process as well. So we're, again, at 1500 degrees C and various temperatures, and nobody wants to put that in their downstream equipment. So we go through a throat, which kind of funnels that flow into the center of the radiant syngas cooler. You've got a lot going on from a modeling perspective, of course. You've got particulates, you've got CO. You're still reacting. You're above the point where the water gas shift reaction freezes at the start of the radiant syngas cooler. And then you get down to the water sump where we are trying to collect as much of the ash and solids as possible. So you're still at a very hot temperature, so you've got evaporation occurring there at that water interface. Those gases are somewhat soluble in water, not depending on which one we're talking about. Of course, CO2 is very soluble, hydrogen not so much, but still not zero. And then you've got ash falling into that water sump. You can form salts down there. So I think that kind of gets to the point on the right-hand side of, there's a whole lot going on here from a modeling perspective. You've got the thermal aspects, the chemical aspects. It's transient, it's three-dimensional. You've got gases and particulates at the inlet. You've got all those thermal walls for heat extraction. You're losing a little bit of heat out the reactor, but you're pulling it out intentionally in the radiant syngas cooler. And then you've got the water sump. So there were a few simplifications taken. They didn't really consider reaction of ash with particles. Only the carbon particulates are in the reaction for the simulation. And then they also simplified and didn't evaluate the evaporation, solubility, or salt formation on the water sump. And then I forget, is this where we transition, Sam? Oh, perfect.
So this was a really interesting project to work on with Arvos. And the team in Germany was super knowledgeable, and they were able to help us a lot because they had some previous experience with this reaction set. And so the goal here was we have this mixture of gases coming into the vessel, and the Arvos team knew that they wanted to have this GRI Mech 3 chemistry set implemented in Barracuda. However, this is a much larger set of chemistry than what we've, as far as I know, than what anyone has put into Barracuda before. So this has 325 reactions involving 53 gas species. You can download this online. There's on the Berkeley website, there's a whole collection of pages that are dedicated to this, and you can download it in a ChemCin 2 format, which is kind of painful to parse. if you've ever tried to do that before. And so we wanted to bring this into Barracuda in order to include it in the model. One thing that I found kind of early on, I was starting to go down the path of writing my own KimKin2 conversion code in Python, and thankfully my Googling led me to an open source tool called Cantera. And so this is a tool that can deal with chemical reaction kinetics, thermodynamic properties, material properties, things like that. And so Cantera actually has GRI Mech 3 built into its distribution as kind of the primary example that they use to teach people how to use Cantera. So this was fairly lucky, and I'll take the luck when I can get it. And so what we ended up doing was learning a little bit about how to use Cantera, but then writing a set of Python scripts that could query the GRI Mech 3 information and write out text files that included base material definitions, reaction rate coefficients, and reaction definitions for Barracuda. And this could be generalized to other chemistry sets too, right? So like if you have a chemistry set that you know you're going for and there is a KimKin2 format file available, we could potentially use this same strategy to read that into Cantera and easily access the pertinent information and generate the portions of the Barracuda project file. And the reason we want to do this is because it becomes very, very painful to enter this many things in by hand. So here's the Barracuda GUI that I'm showing. This is the set of reaction rate coefficients. And what we ended up doing here was there are 325 reactions. All 325 are forward direction, but 309 of those are also reverse reactions. And so what I did is I split it into forward and reverse. And so in the end, there's 634 reaction rate coefficients that need to go into Barracuda, and 634 reaction expressions that need to go into Barracuda as well. So you don't want to enter this in by hand. It would be very error prone and very maddening. And so it was nice to have this programmatic way to get this really big reaction set and put it into text file format. And the Barracuda project file is basically a big text file. So you can build a project file by combining these different text files that were generated. One thing that I always try to preach to people is when you do something crazy like this with chemistry, you should definitely run a single cell Barracuda simulation to verify this, because there's very little chance you're going to get it right on the first try. And as I mentioned, the Arvos team had some deep experience with this reaction set already, so they knew what to expect under specific conditions with certain pressures and temperatures and gas compositions. So we are able to verify that we are getting the reaction rates calculated in the right way after all this information was in Barracuda. One thing that was really critical to enable us to do this, and this has not always been in Barracuda, but it's been in there for several years now, and I don't remember the exact version where this went in. But we have this concept of user-defined expressions. You can use user-defined expressions to define drag models. You can use them to locate boundary conditions, and you can also use them to define chemical rate coefficients. And so the GRI Mech 3 reaction set, it includes some kind of tricky kinetics that would not fit into just a typical Arrhenius format. So we have three-body Arrhenius, we have these different fall-off reactions where above a certain pressure it behaves one way and below a certain pressure it does something different. And so some kind of complicated things. Most of the reverse rates have these Gibbs free energy expressions that would be not possible to represent unless you have something like this user-defined expression language where you can put all of this into Barracuda. So it enabled us to get this reaction set in and run successfully. One thing is that this is a very large reaction set, and it was also a large model. As you saw, it's like very tall vessel, and we needed enough cell resolution to capture the spatial gradients, and so it had about 780,000 real cells. The number of clouds was somewhat low, right? It was pretty dilute in terms of the actual mass flow rate of particles going through this system, so it's not a really impressive cloud count. But with all of this and running on one of our newer machines at CPFD, we were using 2 RTX 6000 GPUs in combination. We were getting about 3.5 seconds per day, and we found that we needed to run, probably 40 to 50 seconds to get to a steady state operating condition. So we said, okay, we're going to set an in time of 60 seconds, and so that took about 16 days for reaching that point of simulation time. So kind of a challenging simulation, definitely challenging to set up, but in the end, a really interesting experience and a good experience working with the Arvos team. So I think now I hand it back over to Eric.
And just to go through some of the results with you, we took a flux plane between the POX reactor and the radiant syngas cooler and compared our simulation results with the Barracuda virtual reactor simulations. And you can see on the x-axis is the simulation time, not reactor residence time. But within 10 seconds or so, it was in very good correlation on those 4 key components being hydrogen, carbon monoxide, carbon dioxide, and water. On the next slide, we've got some various animations shown. So on the left-hand side is the fluid temperature, fluid speed being the second simulation. The middle one is residence time in seconds, particle temperature being second to the last, and then mass fraction of carbon being on the far right-hand side there. I think you can see that it's certainly not a very simple and idealized system that's actually going on inside there. Personally, I think it's easiest to see on the mass fraction of carbon that what's going on there as far as turbulent flow and conversion of those small carbon particles. On this slide, we're taking a look at the heat transfer in the radiant syngas cooler. There was a couple of different approaches taken there. First, they used the heat flux as a boundary condition in the radiant syngas cooler. The real area for improvement in all of this was the heat transfer, or the radiant heat transfer specifically in the top section of the radiant syngas cooler. So there was quite a difference between the wall temperature that we estimate versus what the Barracuda simulation estimated. There's definitely some backflow that occurs in that system. It was evident in those videos as well. So you've got a fairly cool gas on the surface there, but in A1 area, you're going to have your highest temperature. So of course you'll have your highest radiant heat transfer there. So still some areas for improvement, but overall, it was very good correlation as far as heat transfer as well, as you can see on the second and third graph there on the right-hand side and in the center as well. So the reference case that was used was a similar radiant syngas cooler geometry that was simulated using ANSYS CFX. And that matched well with our internal tools. The convective heat transfer has the same shape, or no, pardon me, I got those backwards. Convective heat transfer, really good correlation between our tools and Barracuda tools, as you can see on the graph on the top right. As far as the radiation heat transfer, the curves are the right shape, but there is a difference between the two as far as the overall transferred heat. So there's still some work to do there, or opportunities for improvement, but hey, everybody can improve, right? So as far as conclusions, this was the first implementation of GRI Mech 3 within Barracuda. And on that previous slide, he mentioned 325 reactions. That was the forward reactions. There's another 309 in the reverse direction, so it's a total of 634. Way too much to be typing in by hand, of course. The gas phase reaction results at the POX reactor outlet were very consistent with other models that we've developed and validated with, in our company. The reaction rate and conversion of carbon particles also was well confirmed with previous work that we had done. Also provides a better understanding of fluid particle flow and particle separation within the equipment. And the area of improvement is further work on as far as the heat transfer. And with that, I will stop talking.